quickly. Now the next one, again I don't know whether you have done this one or not. This is quite simple part. U of nu comma t d nu. Okay. So this was energy density per unit frequency range. If you multiply by d nu, this is energy density. Okay, this total is energy density, not per unit frequency. You are multiplying with frequency. Per unit frequency multiplied with frequency. This total is energy density. You have written this one 8 pi nu square by c cube h nu by e power beta h nu minus 1, where beta is equal to 1 by kBt d nu. Okay. Now if you want to convert this one in terms of lambda, look at here, you can write this expression u of nu comma t d nu. So this is energy density. This total is energy density. Okay, in the frequency range. It's not per frequency. I have already multiplied by this is per frequency. Already multiplied with this one. That's why this total is energy density. The same thing is equal to u of lambda comma t d lambda. This is energy density per wavelength into wavelength. Total is energy density. Okay, you will understand this one in statistical physics. I do this kind of stuff in many cases. Okay, now look at here in this one. So what I do here is to write the whole thing in terms of lambda, u of lambda comma t d lambda, that's equal to u of nu comma t d nu. What I do is I will do d nu by d lambda into d lambda. Nu is equal to c by lambda. So, but I put mod here, okay, because this derivative may introduce negative sign. Okay, I may put mod here. So again, so d nu by d lambda is equal to mod is, that is c by lambda square, isn't it? Minus c by lambda square, but I am taking mod. Okay. So then 8 pi nu is equal to c by lambda the whole square by c cube hc by lambda e power beta hc by lambda minus 1. What is this one? C by lambda square t lambda. You have converted in terms of lambda. Whole distribution in terms of lambda. Try to rewrite. Okay. I hope you can take this logic. Quickly grab that one.
So this is always equal, right, sir?
These two are equal. Because this total is energy density. Again, this is per wavelength, this is per frequency. But once you multiply this with this factor, those will be equal. We do this stuff very frequently in statistical physics. Okay, you may not remember now, but after that you will remember that trick. Quickly, again, yesterday I gave one problem. Photon cannot be absorbed by the free electron at rest, isn't it? Photon cannot be absorbed by the free electron at rest. That's why photoelectric effect cannot happen with a free electron. It should happen only with a bound electron. Okay, I'll give some reference regarding this photoelectric effect and Compton effect. You try to study that one. That's quite lengthy. I mean, at what wavelength, at what energy of the photon photoelectric effect happens, and what other energy of the electron, for what other energy of the photon Compton effect happens. Okay, and it all depends on the material also, actually, Z value of the material also. Is that okay? Now look at here. Yeah. Now what you call free electron at rest. Free electron at rest cannot absorb photon. So there are two approaches here to prove this one. So I hope you have tried that one. Let me check your homework later. So first one is non-relativistic. Okay, I'll just mention one more book later. It is mentioned very well. Non-relativistic. Look at here. If electron was at rest, again you can take moving electron. Free electron means it can be moving electron also, but in the simplest case I am taking electron at rest. Okay. So now suppose electron is at rest. Okay. So it is absorbing photon of energy h nu. Okay. Then after that one h nu should be equal to half mv square. Non-relativistic kinetic energy. Before it is rest, because of conservation of energy, So electron is what you call absorbing photon. Is that okay? So similarly, conservation of momentum says, look at here, before you have electron at rest, you have photon, okay, of energy E is equal to h nu, momentum P is equal to h nu by c, okay. It is at rest now, non-relativistic, you don't take any rest mass here, like that. Is that okay? So now, so this is energy conservation, so then momentum conservation says h nu by c is equal to m into v. So before, after suppose photon vanished, but electron is moving here with velocity v, so that kinetic energy will be half m v square, momentum will be m into v. Is that okay? Before and after, momentum should be conserved, kinetic energy should be conserved. Take the ratio 1 by 1 by c, m got cancelled, v by 2, v is equal to 2c. That cannot happen. Is that okay? That cannot happen. Quickly. So try to do it yourself. Take it as a hint. Okay? Remember, in any particle interaction, conservation of momentum and energy is always happens. Okay? Again, we shall see this one in particle physics. Okay? Conservation of momentum and so energy, that is what you call momentum and energy are always conserved. Okay? Linear momentum and energy are always conserved. Whatever the particle interaction you take, this is also kind of particle interaction. We shall see later, Compton effect also. Okay? So relativistic approach. Okay? So suppose h nu is equal to, after that one, again don't write kinetic energy, write relativistic kinetic energy. Initially it was at rest, right? Relativistic kinetic energy. I hope you know this one. I'll just talk about this one. P square c square plus m square c power 4. Okay? me, mass of the electron, rest mass, okay, minus me c square. Okay? So again h nu by c is equal to p of the electron. I better to specify, am I right? Pe. Pe, isn't it? Now if you write Pe, look at here, that is let is equal to, wait a second, so h nu is equal to Pe into c, isn't it? Look at these two expressions, how this can happen simultaneously. This cannot happen simultaneously, isn't it? Again, if this term, these two terms was not there, you can write h nu is equal to Pe into c. These two cannot happen simultaneously. Are you getting my point? So from momentum conservation you got one equation. From energy conservation you got, this is a kinetic energy, total so energy of the free electron, relativistic energy of free electron, so subtracted with rest mass energy. Is that okay?
Yes.
So there's a kinetic energy, relativistic kinetic energy. We write like this. I'll come to that point later, or again we will discuss that one. Any problem in live chat in YouTube? Again, after photoelectric effect, again, Einstein said that a radiation composed of a particle called photon, a photon have got energy E is equal to h nu, isn't it? And I think they also said photon has a momentum E is equal to h nu by c, but that cannot be verified in photoelectric effect, because photoelectric effect is an absorption process. So where would you verify momentum and all? You will verify momentum only in case of collision event. So that's why photoelectric effect will not completely or it will not satisfactorily explain photon nature. I mean, it will, because we don't have other choice, as we have discussed yesterday. You can't explain that one by wave theory or wave, so again wave nature of light. You should consider light composed of a particle, and one photon meets one electron, and electron absorbs photon. In that absorption event, photon vanishes, and completely that photon energy will be transferred to electron, and it will come out. If photon energy is greater than work function, it will come out, otherwise it will not. We can explain the whole story of photoelectric effect using photon theory. I mean, again, one more very important part is frequency will decide the energy of the photon, and intensity is proportional to number of photon crossing per unit area, like that. Is that okay? So those are the concepts. Now again, in Compton effect, along with this one, along with again, so particle theory of light, Along with this one, we can verify that photon has a momentum h nu by c. So once we define photon as a particle, now the question comes, what is the mass of the particle, isn't it? Somewhere I think I quoted again, photon mass is not defined at all. We better to say like that. We better to avoid the concept of mass of photon. We don't need that one. We don't need that one because so velocity is not most general term. Again, we see that one in so classical mechanics. Momentum is most general term. So momentum is equal to mass into velocity. Again, so that's why we can directly define momentum without getting into, again, velocity of the photon is velocity of light itself, but we will not talk about mass of the photon. What we say is we directly define momentum like this. Now we will never write this one as mass into velocity like that. Is that okay? So we just take this is the momentum of the photon, h nu by c. So now mass, concept of photon mass absent actually, and we even without taking concept of mass of the photon, we can do all calculation without any what you call loss. So that's why sometimes we say rest mass of the photon is 0. So that means photon cannot exist at rest. It doesn't mean you can so weigh its weight or something. It means photon cannot exist at rest actually. If you try to make photon again, so to be at rest, it will vanish. If you consider it as a particle, so you can't keep photon at rest. It should move with high speed, so velocity of light, in order to exist. I think in its own reference frame, time is static, isn't it? According to relativity. Am I right? Because it is moving with a velocity of light. If something moves with a velocity of light in its reference frame, time will be a kind of static, isn't it? So what is the lifetime of photon in its own reference frame? Not in its own reference frame. What is the lifetime of photon? I mean, if it moves with the velocity of light, it will move for a long time. Again, it will not decay or it will not vanish as it is. Is that okay? Again, my idea is if you are trying to stop that one, or if you can't keep the photon at rest. That's what I'm saying. You can't keep photon at rest. It is moving with the velocity of light c in space. So that is the thing that I want to put. Now, so Compton effect verifies that photon has energy E is equal to h nu, and photon has momentum h nu by c. After Compton effect, again photon theory is boosted up actually. Now let me quickly take the derivation and the experiment. Again, they have used X-ray photons into, I don't know what is the target that they have used. You can go through Jetili book here. Yeah. So now X-ray photons which are scattered by electron. Now look at here. It is like this. You have electron here. You have electron here which is at rest. We consider electron to be at rest. What you do is you will incident photon on it. You will incident photon on it, and I'll because we haven't seen photon, I'll call this one as photon. Is that okay? And that energy of the photon, incident radiation h nu, nu is equal to c by lambda. Okay, lambda is the wavelength of incident radiation, incident photon. Let me say like this. So momentum is equal to h nu by c. It is incident like this on the electron. This is before collision. Before collision. Now after collision, what would happen here is, let me draw it here. So suppose photon will travel in this direction. Is that okay? So electron will be recoiled in this direction. It's just playing a carom board. Where your striker is very light, then peace. Can you say like that? Because it is at rest. If you strike that one with a striker which is very light, and that striker is deflected with a various direction, and if you calculate its energy of the scattered striker, it will be different for different direction, and exactly same thing is happening here. Let me argue first. So let me call this one as theta, and electron is recalled here. Electron is recalled here. Okay, this is electron, this is electron, this is proton. Now the scattered proton have got energy E prime, that is equal to h nu prime, and its momentum is equal to P prime is equal to h nu prime by c. I'll call this one as phi. Okay, I'll call this one as phi. That is needed for some more problem given in Jatili. Okay. Yeah, I'm expecting some question in GATE exam. That's why I'm doing that one. Okay. It's a kind of carom board experiment, isn't it? Look at here. And again, for different theta, what they found is its energy or its wavelength depending on theta. So again, that is similar to when you have a striker which is very light compared to piece of your carom board. If you strike that one, that striker will deflect in a different direction. If it deflects in a different direction, it will have different kinetic energy, velocity. The similar thing is happening. The photons which are scattered in a different direction had a different energy, or the light whatever you received, or X-rays whatever you received in a different direction have got different wavelength. Now let me just apply conservation of what you call, it's a kind of particle interaction. Okay, we shall study this one in particle physics also. So this Compton effect. Now conservation of momentum says, look at here, suppose if I take P vector is the momentum of incident photon, is that okay? It's along x axis actually, but let me not quote any axis or something. Let me just again, without that one I can do that one. Okay, so initially momentum of electron is 0. Okay, so P vector prime, that is momentum of scattered photon, and initially its kinetic energy is 0, or its momentum is 0, electron is at rest. Now again, capital P, okay, capital PE, this is momentum of, can I call it as recoiled electron? Recoiling electron, this one. Is that okay? Let me just write it here. Now I have written energy, momentum, and I have defined momentum of this electron. How do you define energy of this electron? Energy of this electron. I think I better call EE, isn't it? Energy of this electron. So now that energy of the electron, again you should use relativistic formula, because the whole thing again very small particle, microscopic particle, and velocity will be very high. So that's why you should use relativistic formula, not again ordinary half mv square or something. Is that okay? So again, let me take that relativistic energy directly. That is root of Pe square c square plus me square c power 4, where me is rest mass of electron. I hope you know this one. Okay? Yeah. Wait a second. He's asking, photon vanishes after collision. Why we take direction of the photon after collision? Okay. Now look at here. Photon can need not to have absorption process always. That was photoelectric effect, where absorption dominated actually. I better to say like that. Those are probabilistic event. Even if you take UV light, there may be a minute probability of happening of Compton effect actually, but it may be very low. So if you take X-ray region of radiation, then there is very less probability of happening of photoelectric effect. I think in nuclear physics we study about a photoelectric cross section, Compton effect cross section like that. That cross sections will talk about probability. Okay, so that's a good question. It's a collision event. It's not absorption. In X-ray region, probability of happening of photoelectric effect is very low. I think I need to have some more logic to explain that one right now. I think, yeah, that's a good question. a photon is not losing its energy. Yeah, it is losing this energy definitely in this kind of collision event, because this is lesser. This should be lesser than this one, just like how you play with the carom. Is that okay? Again, but it is transferring some momentum to this one, that we can say like this. It's a kind of so transfer of some momentum to electron which were at rest earlier. Is that okay? Now, we again, because of I think X-ray region, this Compton effect is dominated. Are you getting my point? Not photoelectric effect is not happening here. So that's a good question. So now in this one again, we should take relativistic energy. I have taken this formula directly. M is rest mass of electron. Okay. Now look at here. So now I have to apply two conservation. Now one is conservation of momentum, other one is conservation of energy. Conservation of momentum says momentum of the photon, incident photon, that's equal to, I think I have defined the symbols, that's equal to momentum of the scattered photon plus momentum of the electron. Now here we don't need this momentum of the electron. Now look at the calculation. In the whole calculation, we don't need this one. What we need, again, what we are measuring, we are measuring this theta and this wavelength, isn't it? That wavelength is decided by P dash or E dash or nu dash, isn't it? Those are all related. Yeah, I think I need some more input to answer why we need to use what you call X-ray only. Okay, so let me check it out.
Sir, electron wavelength and this photon what we incident, these should have equivalent wavelength. Then only the scatter will happen. Otherwise, if you take just electromagnetic wave, it will have more wavelength. So it is negligibly small, that wavelength of electron.
I mean, no, it's a scattering event, isn't it? You are again, you are talking about the situation of a diffraction kind of thing, where incident wavelength should be comparable with the.
That, then only it will see the electron. When the electron is there, then only it is scattered.
Yeah.
If I have more wavelength, so scattering will not happen.
So scattering will not happen like that. Okay, so that's a good reasoning, but let me check out. Let me check out what is the proper reasoning behind. Again, it is studied in nuclear physics, as I remember, some different cross sections. Okay, yeah. Yeah, let me try to answer that one. Okay, why we can't do this one with the low energy? What is the proper idea? He is quoting that wavelength is, when wavelength is higher, it cannot happen like that, isn't it? Yeah. That's not again. There is one reasoning that so they are giving is X-ray energy is more, so that electron cannot absorb its whole energy. You can't say like that, isn't it? I mean, okay, X-ray energy is very large, isn't it? So that's why electron again, for photoelectric effect we don't need that much energy. We need of the order of couple of electron volt, isn't it? X-ray is very high energy. What is the energy range? Any idea? I think hundreds of electron volt or 50 electron volt, like that, 50 or 100 electron volt. That is the X-ray energy, isn't it? So that's why I think again, for photoelectric effect to happen, that is not that much energy is not required actually. But still, why it is not happening, isn't it? That's the question. That's a valid question. Let me try to answer that one, because why that is less probabilistic. Now look at here. Once you treat this one as a particle, you don't have to think about wavelength at all. I mean, particle interaction, isn't it? Whether it is UV visible or X-ray, isn't it? It doesn't matter. I think we should explain by some other means. That's what I'm thinking. Yeah, that's a good question. Yeah. Again, in gamma ray region also, this probability becomes very low. This probability is very high in X-ray region. That's what I'm thinking. Let me quote some nuclear physics chapter. Okay, that's a good. Yeah, again, this is a kind of assumption. Okay, by assuming electron is at rest in the atom, but that's very good, because when you compare speed of light, I mean, when you compare speed of the photon, the assumption of electron is at rest is okay actually. Is that okay? Yeah. Now look at here. I have applied momentum conservation rule. momentum conservation. So now I don't need this PE. I should avoid this one. That's why I'll solve it for PE, because that's we can't measure this one anyhow. So that's equal to a P vector minus P dash vector. Is it okay? So now in this expression I have PE square, isn't it? Square of a vector is nothing but dot product with itself. I think I explained in vector algebra, isn't it? So a PE square, you can write as PE dot PE. PE dot PE. Actually, I should not have rubbed this diagram anyway. So that is P prime P minus P prime dot P minus P prime, isn't it? When you take this dot product with itself, what will happen? P square plus P dash square minus 2 P dot P dash. Now this was the direction of P, okay? This was the direction of P dash, I mean scattered photon, isn't it? The angle between them in our diagram, I have taken theta. When you take dot product, what will happen? P square plus P dash square minus 2 P dash into cos of theta. Is that okay? Let me keep it one side. Let me keep it one side. Wait a second. I better to do small manipulation here. Okay. What is this one? PE square. PE square. Now I'll multiply again. If I take P square is nothing but h nu the whole square by c square, isn't it? P prime square is equal to h nu the whole square by h nu prime the whole square by c square. Okay. I'll multiply whole thing by c square. PE square, C square. Why I have this one, in my energy expression, energy of the electron expression. Okay, let me keep one of the expression here. So when you multiply by C square, what will happen is h square, h nu the whole square plus h nu prime the whole square minus 2 h nu prime cos of theta. H nu prime cos of theta. Now what I do is I want to make it perfect square somehow. So that's why I'll add 2 h nu prime and I'll subtract 2 h nu prime. That okay. To the whole expression I'll add plus 2 h nu prime and I'll subtract 2 h nu and h nu prime. I'll combine these three. A square plus B square minus 2ab, A minus B the whole square. And I'll keep that expression. Again, since I have already done that one, I know how to do that one, okay? How to proceed with that one. Now that is equal to, again, this momentum conservation that gives PE square C square, that's equal to, I can write h nu minus h nu prime the whole square. So now here 2 h nu prime you can take common, you can write 1 minus cos theta. Isn't it? 2 h nu prime you can take common, you can write 1 minus cos theta. Just check it out. Yeah. So I'll keep it one side. I'll keep this expression one side. Other expression is energy conservation. Energy conservation. In particle physics, all particle interaction are conserving these two, isn't it? So relativistic momentum conservation, relativistic energy conservation. Yeah, we better quote like this. In particle physics, we quote it like that. Okay, but relativistic momentum conservation and relativistic energy conservation. And this is also particle-particle interaction only. If you take, again, it will confirm photon nature, but if you take incident one as a photon already, then it's a particle-particle interaction. So now energy conservation, incident energy is h nu, so incident photon. So but you had electron before the reaction, it was at rest, its rest mass. This is the total energy before the collision. After the collision, after the collision, photon energy is h nu prime, and your energy of the electron is Pe square c square plus me square c power 4. Now solve this one for Pe square c square. Solve this whole expression. That how to do that one? So Pe square c square plus me square c power 4, that's equal to h nu minus h nu prime plus mec square, the whole square. Just check it out. Is that okay? I have taken it here and I squared. Now if you square this one, I will keep this one side, h nu minus h nu prime, the whole square, a square plus b square, me square c power 4 plus 2 times ab, 2 times h nu minus h nu prime into mec square. Just check it out. Pe square c square plus me square c power 4. Now I can cancel this out. No, I mean we can solve the equation for momentum of recoil electron, okay, but we are not interested to do so because that's not measurable quantity in our experiment, okay. Again, it is there in Jatili. He mentioned that one in a problem, how to find kinetic energy of the recoil electron and all, okay, in the problem. You can just check it out. Now when you compare these two, is that okay? The whole thing is Pe, again let me write it here, Pe square c square is equal to h nu minus h nu prime, the whole square, so plus 2 times h nu minus h nu prime into mec square. Just check it out, into mec square. Is that it? Any other manipulation? I think yeah, that's correct. Is that okay? Now when you compare these two equations, you can subtract or you can equate these two parts, isn't it? So that what you get here is, so 2 times mec square, h nu minus h nu prime, I will take h outside, I will write c by lambda minus c by lambda prime, nu minus nu prime, c by lambda minus c by lambda prime. Is that okay? Nu is equal to c by lambda, nu prime is equal to c by lambda prime. Don't write c prime, okay? I mean both of them will move with the speed of light only. So that is equal to 2 h into h, nu into nu prime, that is c by lambda into c by lambda prime into 1 minus cos theta. Now if you manipulate, again you can cancel out this one, isn't it? C square. Now if you take LCM and if you rearrange, look at here, when you take LCM, what will happen here is, so C lambda prime, yeah, any mistakes? No, lambda prime minus lambda, isn't it? C outside, me, I think I have cancelled out c square, me into c, isn't it? That's equal to h by lambda prime into 1 minus cos theta. Now this got cancelled. Lambda prime minus lambda, we call this as Compton shift. If energy of the photon decreases in process, wavelength will increase. I mean wavelength of the scattered photon is higher than wavelength of incident photon. So that's why this should be positive quantity. You can expect like that. So that's equal to h by me into c into 1 minus cos theta. And we call this h by me into c as lambda c. Again, you should know this one. Somewhere in some GATE exam, they directly ask this question. Only in GATE exam, they may ask some question on direct formula actually. So what they write is, they define is lambda c, that is h by rest mass of the electron into c. Those are constants, isn't it? You can just evaluate that one. I think its value is 2.426 into 10 raised to minus 12. 2.426 into 10 raised to minus 12 meter. This is called as Compton wavelength. This is called as Compton wavelength. You should remember this one, okay? And we can write again, this is, we call this one as Compton shift, change in the wavelength, okay? So delta lambda, that's equal to wavelength of scattered photon, because scattered photon have got less energy. So that's why it has more wavelength. Lambda prime minus lambda, that's equal to, so lambda c into 1 minus cos theta. Sometimes we prefer writing that one in terms of sine square theta by 2. 2 lambda c sine square theta by 2. We write like this sometimes. Now look at here. This wavelength shift, that depends on theta. I mean, if you measure photon wavelength or if you measure X-ray wavelength at different angle, this is the incident one, isn't it? This is the scattered, so this is incident X-ray, this is scattered X-ray. If you find wavelength of the scattered X-ray at different angle, this equation is satisfied. Again, this equation can be seen with the experimental data. So now, because of that fact, again, whatever the assumption we have done, since this whole formula, it will satisfy experimental data, the assumptions are true. What are the assumptions? Incident one was a particle, it was, so we call that one as photon, it has a momentum, it has an energy, and it's again, it's a, look at here, we have applied all just particle-particle interaction process, isn't it? So that's why, again, just like our, so classical physics, in just like we do in case of collision, we did the calculation. So that's why this one, I mean, after Compton effect, there was not much question about photon nature. I mean, nobody had a doubt. Is that okay? Yeah, any question quickly? You can find recoil momentum also, okay? It's just elimination of quantities, isn't it? Again, I eliminated momentum of the photon, okay? That kind of thing we do in particle kinematics. So in particle interaction, finding the kinetic energy of one of the product, finding momentum of the one of the product like that, okay? Now do these two problems. One is example number 1.3. Okay. Example number 1.3. Along with that one, do one more problem given at the end of this one. Today I am going to assign problems in Google Drive, sorry, Google Classroom. You should submit the homeworks, okay? Wait a second. That is, I think, problem number 1.5 outside the chapter. 1.5, 1.6 and 1.7. 1.5, 1.6, 1.7. Because similar calculation we use in particle interaction, again using conservation of momentum and energy and eliminating one part and solving the equations for other part like that, okay? That practice is needed. Do these three problems. These are solved problems, okay? These are solved problems. Evening, if I save some time, I will take couple of problems, okay? Solved problem, you can solve it. Any question quickly? Now after this one, now recoiling of electron will be, yeah, again if theta is equal to 180 degree, we call that one as, again they are designing question in GATE exam. If you take theta is equal to 180 degree, that means photon is coming back, isn't it? In that situation, your delta lambda is equal to, I think, 2 lambda c. Am I right? Cos 180 degrees minus 1, 1 minus of minus 1 plus 2, isn't it? In that situation, definitely electron should recoil in the forward direction. It will not recoil in the backward direction. Photon can recoil in the back. Again, photon can rebound in the backward direction. That will happen actually. I think as I remember, they designed some question. I'll provide those questions, okay, in GATE exam. No, again, wave theory cannot explain the whole process of Compton effect at all. The question is why we are taking particle interaction, why not considered as wave interaction? Is that okay? Wave theory cannot explain. Now look at here. After this explanation, you should have no doubt because it's a kind of Karen board experiment, isn't it? You can't explain this one using any wave. Yeah, photoelectric effect as well as Compton effect. We cannot. Yeah, we cannot explain using wave property. That's why again particle property is boosted. And after this experiment, after that Compton wavelength, which depends on theta, Compton shift, which depends on theta. Again, look at the assumptions we have done while doing this derivation. Now, the last expression which satisfies the experimental fact. That's why assumptions were true. That's how we argue. That's a good question. I mean Compton wavelength for photon. Mass of the photon is 0, then it will be infinity. That's what you are expecting. Now, Compton effect is interaction between again photon and electron. Is that okay? Again.
Interested to know about electron nature, right?
Yeah. So, which shell Compton effect happens? I think I need to work on that one. What exactly the chemical that they are using? What is the target that they are using? Any idea? We should check out the target that they are using. This can happen with inner shell electron also. I have to check out which target that they have used in the original experiment. According to that one, we can think of electronic and configuration.
Is it necessary to know the target? Because in quantum we generally think like electron is.
Yeah, electron is at rest, isn't it? We are taking electron is at rest. It doesn't matter whether it is free electron or bound electron or something. If you take metal, usually free electron will contribute because they are abundant. So in the metal. No, again, that's good question. Frequency and wavelength we are using, those are wave property, isn't it? Yeah, if they are metallic block, most of the case it is free electron only. Again, whatever the interaction happens, that happens with the free electron only. But it can happen with the core electron also. Somewhere I read that one. Let me try to code that one. Just post all of these questions again into Slack. Okay. Any unanswered question here, post it into Slack so that I will search and answer that one. Okay. Yeah, that's a good question. Frequency and wavelength that we are using, those are wave property. Okay, wait. I'll come to that one, isn't it? No, again, you can define de Broglie wavelength of photon. If you consider light as a particle, why can't you define de Broglie wavelength of photon?
I am saying like de Broglie wave is consisting of two things, left side, right side. Left is wave property, right side is particle.
Particle property.
Momentum, we are dealing with particles.
No, not like that. We have some other means of explaining that diffraction and interference. I mean, probabilistic way. Again, after that one, again, we shall have this discussion. That's a good idea. If you use other region, again, I think you joined later. If you use other region of the radiation, this probability is very low. Let me quote some, I think R.D. Evans, okay, Nuclear Physics by R.D. Evans. In that book, I read about cross sections. Okay, I think in Crane also he might have mentioned. Let me check out. Shift depends on lambda prime minus lambda, that's equal to h by m e into c into 1 minus cos theta. This shift depends on this lambda also. Okay, if you change this lambda, then this lambda minus lambda prime will change. It depends on incident X-ray wavelength also, isn't it? If you choose different one, then that shift will be different. Okay. No, it is like this in the resultant direction. In different directions, you find different wavelength. That's what I'm saying. In the scattered direction, if when you vary theta, your wavelength will be. Yeah, rest of all things are constant. It depends only on theta. Depends only on theta. Yeah. Yeah, so that's a good argument. He's saying that energy of the X-ray photon is around 70 to 20 kilo electron. Kilo electron what? Yeah, maybe. Yeah. So which is very larger compared to that photon energy. Electron can be considered as free because electron bound energy is some minus 13.6. So electron out like that, isn't it? Compared to the what you call energy of the incident photon, electron can be treated as free. That's a good argument. Yeah, from Wikipedia. Thank you. So let me move on. Wait a second. One question is remained over there. That's the question was even though we define frequency and wavelength again, those are wave property. Again, look at here. It is like that. Suppose just think that frequency and wavelength decide color of the photon, color of the light, and light composed of photons. Can you imagine like that? Yeah, earlier we explained all of the phenomenon using what you call so using wave theory, where we defined frequency and wavelength. Now I'll say frequency and wavelength, those will decide what you call color of the light or something, and light composed of particle. So called photon. I'll assume like that. Now, while thinking about photons, I'll never think about what you call wave or something. While thinking about photon, its energy is decided by frequency. That's correct. Its energy is decided by frequency or wavelength, and its momentum, that's also decided by what you call h by lambda, wavelength or frequency. But once I start treating light composed of photon, I will never think of wave nature, wave behavior or something. I can explain all phenomenon using that one. Even interference and diffraction, we shall study that one. Without so treating wave behavior, we can study interference and diffraction using particle theory only. So that's what again we are going to learn here. Yeah. Next one. So photoelectric effect and Compton effect. Again, this Compton effect was in 1923. Okay, it happened in 1923. Historically, it was not in the beginning actually. Yeah, again go through that Compton effect again. You will be convinced that incident one is a photon. Okay, again do this derivation again. You will feel that one.